Hi everyone, welcome to another session of Physics Latam seminar. Today we are happy to have Professor Jan Manschot to give us a lecture on topological correlators of supersymmetric Young Mills and four-manifold invariant. Professor Jan Manschot is a professor at Trinity College Dublin, the University of Dublin. His research spans quantum field theory, quantum gravity, string theory, analytic number theory, and geometry. So during the lecture, if you have any question, please feel free to unmute yourself or just send them in the chat. Now I will hand over the session to Professor Jan Manschot. Thank you again for accepting our invitation.
Thank you, Jesse. Thank you for the invitation to give these lectures and the introduction. In these four sessions of these lectures, I plan to give an overview about topological correlators of super young Mills and four-manifolds. Feel free to interrupt. I don't have a very good idea, I think, of the background of most of you. So let me know if you have any questions or comments. Happy to take those on board. So maybe just let me start with giving a brief outline of these next few lectures. So for today, I'm planning to introduce a bit of Young-Mills theory and instantons, and then moving to supersymmetric QFT. And then the lecture tomorrow, I plan to introduce topologically twisting for these supersymmetric QFTs and discuss their correlation functions. And then next week depends a bit how it goes, but I plan to consider a few theories on which we have worked quite a lot in recent years. One is the so-called n equals to star theory, which is the kind of the basic n equals 2 theory together with an adjoint hypermultiplet with a mass. And these will be related to Euler numbers of instanton moduli spaces. And then in the following lecture, I will discuss cases of which we abbreviate with SQCD, cases where we have fundamental hypermultiplets with masses leading to invariants known as Segre invariants, and the five-dimensional theory, which leads to K-theoretic invariants. Okay, so that's roughly the outline, and we can just see how far we get. There's no specific point we have to reach. Okay, any questions or comments at this point? Okay, so let's start maybe at the very beginning, just introducing a bit of Young-Mills theory, maybe with a somewhat unusual notation. But we consider space-time manifold X. And in this lecture, we'll just pretty much assume that this is R4, and we'll use Euclidean signature. And we consider a simply connected Lie group G. With Lie algebra attempt to make a Gotek G, and most of these lectures, in fact, we will consider that the group is SU2, sometimes as SO3. That's very simple. Then we consider a Gates potential. Will be one of the key players of the lectures. Or if you're with a more mathematical background, connection. A mu dx mu. So this is an element of the space of of all connections on a principal bundle P. So with P, a principal G bundle. And AP is the set of all this AP is the set of all connections. Okay, we can decompose. It's natural to decompose the gauge potential A mu in terms of Lie algebra generators. So we get a sum over indices little a with TA are generators of the algebra generators. Of the Lie algebra G in representation R. Okay. And from the recall that from the gauge potential we can consider the field strength or the curvature. F mu nu A is the anti-symmetric combination of the derivatives. And then this term with the structure constants, A mu B, A mu C. And the theory is invariant under Gates transformations. Let me recall just the form of these transformations. Maybe that A mu goes to A mu, a different A mu, element of G, U inverse minus U d mu. U d mu U inverse. And this has a simpler action on the field strength F mu nu, which is just conjugation. And in this way, we get an infinite dimensional group of Gates transformations. I denote with this calligraphic G. It's the group of Gates transformation. Okay, any questions so far? Okay, now the action of our theory has the following well-known form. We assume here, in fact, that the group G is a SUN. And the action takes the form 1 over 4G squared with G the coupling constant. And we get an integral over our four-manifold, R4 in this case, F mu nu A squared plus I times the theta angle over 64 pi squared. And the integral with all the indices epsilon, mu, nu, rho, sigma, Fa mu nu, Fa rho sigma. And we sum over all the Gates indices A as well as the spacetime indices mu and nu. We can write this more invariantly in the notation of differential forms and using a trace. So we can write this as the trace over the Lie algebra generators, F wedge star F. That's the kinetic term, plus, was there a question? I theta over 8 pi squared integral over x trace f wedge f. You see here this first term is the kinetic term, which depends on the metric through the star, Hodge star, and this second term, the metric does not appear, and this is a topological term which does not change the equations of motions, but it does keep track of these topological aspects of the of your solution. Okay. It's natural to combine these two parameters we have now, the coupling G and the theta angle theta, in a complexified coupling constant. Usually denoted by tau. The real part is given in terms of theta over 2 pi, and the complex part, imaginary part, is given by 4 pi I over g squared, which is naturally as positive, the imaginary part. So this is an element of the upper half plane H. Okay. Okay, so the field strength, of course, does satisfy the Bianchi identity. dF is equal to 0. Then the equations of motions are d star f is equal to 0. Now we can further minimize within the space of solutions to the equations of motion. One can further go to a sublocus which further minimizes the energy, and these are the so-called anti-self-dual solutions. These are solutions where f is equal to minus star f. And so we see that in this case, the Bianchi identity also directly implies that the equation of motion is satisfied. And to see that this indeed minimizes the action, one can write it as follows. So we have the kinetic term is trace f wedge star f, which is manifestly positive. And we can write this as the integral over x 1/2 trace f plus star f squared, which is also positive because f plus star f is self-dual. And then minus the trace of f wedge f, which is the topological term. So if we fix the topological, if we fix this topological property, this will be the install number up to a certain normalization constant. Then we minimize this kinetic term by setting this to 0, which is precisely the anti-self-dual equation. Okay. Are there any questions? Okay, and these anti-self-dual equations, they are precisely also the other name for it is are the instantons. But these are instantons. Okay. Now, in general, we have we have an interesting solution space to these equations. We'll denote these by mk. So let me just introduce what they are. They are just a space of all connections A in the space of all connections such that f is minus star f, and we fix the incidental number k, which with the correct normalization is given by minus 1 over 8 pi squared integral over x trace fhf. Okay. And this whole set is we consider this a space modulo the group of Gates transformations. Okay, and then there's a people have shown that you get indeed a finite dimensional moduli space of these solutions if you mod out by the space of Gates transformations. And this K is known as the instanton number. Any questions? Okay, and so there are important theorems, in particular if X is a complex manifold, which relate these instanton solutions to kind of subjects in mathematics, such as algebraic geometry, differential geometry. These connections go by are given by the Donaldson-Uhlenbeck-Yau theorem, and were earlier conjectured by Hitchin and Kobayashi. It is the Hitchin-Kobayashi correspondence. So this gives a strong interplay between physics on the one side and mathematics on the other side. Okay, now if we substitute f is minus star f in the action we had, we can see what we get for the action. We get simply 8 I squared over g squared minus I theta times the instanton number k, and this then is given by minus 2 pi I times, we can recognize as minus 2 pi I times the complexified coupling tau times the instanton number, such that the exponentiated action evaluated on these classical solutions is equal to q to the 2 pi I, sorry, q to the k, with q is equal to e to the 2 pi I times tau. So we get in a sense, a very natural parameter, in the sense that the exponentiated action depends holomorphically on the complexified coupling tau for these anti-self-dual solutions. Okay, there are any questions? So there's in general these solution spaces are quite difficult, and in fact, finding solutions is also not a simple exercise. There are some explicit solutions are known. Let me review maybe the most important one due to Belevin, Polyakov, Schwartz, and Tiupin, the so-called BPST instanton. This is an explicit solution for just a flat space. To this end, we introduce a radial coordinate rho of a four-dimensional radial coordinate. Just the sum of I is 1 to 4 xi squared. If we use just the standard Euclidean coordinates. And then this explicit solution is given as follows. We have the Lie algebra generators Tj, or I think I had a superscript earlier. The Tj is equal to 1/2 sigma j for j is 1, 2, and 3. Sigma j are the Pauli matrices, and then we have I think that's enough. And then we write a mu of x is given by minus I rho squared over rho squared plus t squared. And then we get this combination with functions v, d mu vx, v inverse x. I will comment on it in a second, where v of x is a Lie group element, is x4 plus 2i inner product of x and t. This is the inner product runs over these three directions, and we divide by the radial coordinate rho. Okay, and so we see that if we take this is an explicit solution. You can show if you take these derivatives and work it all out that it indeed satisfies the anti-self duality equation. It's not very straightforward. There's a bit of it's a bit of work, but one can show that this is indeed an anti-self dual equation, and one can show that if we go to infinity, take rho very large, then this goes to 1, and then the solution becomes pure gates, and a pure gates connection as a vanishing energy. So we have a finite energy because it falls off fast enough if you go to large values of rho. If you make a schematic plot of the energy profile of such a solution, then it looks something like this. We have that'd be rho and E. It will we get such a bump function centered in this case around 0, and the width is related to this parameter t we have here in the denominator. Okay, so for a large value of t, it will become very, very wide, and for smaller value, it's more narrow. Okay. So far. Okay, so we see we get some idea now about these spaces of solutions. We have this parameter t on the one hand, and we could also shift this solution. Now the solution is centered around 0, but we could center it around another point in space-time. So this gives another way to change in a sense we get a moduli space of solutions for these anti-self dual equations. So we have the parameters, we have t, giving the width, and then we can send x mu to x mu minus capital X mu gives us another these parameters to play with. You could also rotate. This gives you 3 more parameters, so you would get 8 parameters in total. Okay. This instanton solution as you see it is only a single bump. So this BPST instanton has instanton number k is equal to 1. If you want to consider instanton solutions with a larger k, you can start from a superposition of these solutions where the centers are far away, and then let's see what you need to do if they come come closer. Okay, and so these solutions are widely studied by physicists and mathematicians. There are various aspects. If you want to do it really properly, introduce these modelized spaces, you have to consider aspects of what happens if you send t to 0. And another thing is if you have multiple instantons, what happens if you have coinciding centers? And I won't go into much detail here into these aspects, but this leads then to compactifications of modelized spaces, singularities in the modelized space, etc. But just to kind of point to these non-trivial aspects of the theory. Okay. All right. Any questions possibly at this point? Okay, so we would like to move towards supersymmetric quantum field theory. On the one hand, you could motivate this of saying that if we want to consider a quantum field theory which localizes to these instanton solutions, then we can learn more about instantons and their the modelized spaces, as we will see. On the other hand, you can also, if you're motivated in supersymmetric quantum field theories, then we'll see that these instantons, they give non-perturbative corrections to the effective action. And if you want to understand the effective action, then you will also need to understand these instantons in detail. Okay, so I will next introduce a little bit about spinors on manifolds and introduce then the field content of these n=2 supersymmetric theories, and then introduce the Seiberg-Witten solution. Okay, so let us start with let me start by introducing a spinor bundle. So a spinor bundle we can understand as a bundle which is associated to a specific representation of a principal spin 4 bundle, which is compatible with the tangent bundle. So let me spell this out in some detail. So we start with a representation of spin 4. Which is a double cover of the rotation group SO4. We consider then the spinor bundle as sub rho over the manifold X. And this is the rho associated bundle of the principal spin 4 bundle and this is compatible with the tangent bundle. So on the tangent bundle, we have the natural action of the rotation group SO4. We can lift this to a spin 4 principal bundle, which is a double cover. Spin 4 is a double cover of SO4. So we require that the spin 4 principal bundle is compatible with the SO4 principal bundle associated to the tangent bundle. And then given a representation rho of spin 4, we form the spinor bundle S sub rho over X. Now the the usual bundles then of two-dimensional spinors. The chiral spin bundles are then associated by the two-dimensional representations of SU2 associated to, if we write spin 4 as SU2 plus times SU2 minus, either the SU2 plus or the SU2 subgroup of spin 4. Chiral spin bundles. S plus minus X are then associated to the irreducible two-dimensional representations of SU2 plus minus on we call spin 4 is the product of these two groups, SU2 plus times SU2 minus. Okay. Okay, so just to, I'm introducing this, of course, because a supersymmetric theory involves both bosons and fermions related by the supersymmetry. And the fermions are spinors or have half integer spin. So we are considered interested in n equals 2 supersymmetry here. And which means that we have another SU2 group in the game, besides these SU2 plus and SU2 minus, which is the SU2R symmetry group. Which is the symmetry which rotates the two sets of supercharges. For n equals 2 supersymmetry, we have two sets of supercharges, which are rotated into each other with the SU2 R symmetry. So this gives us now three different SU2 groups, SU2 plus, SU2 minus from the chiral spin bundles, and SU2R. And the fields will form representations of these three groups, SU2 plus, SU2 minus times SU2R. Okay, so we can I'll list the two types of multiplets which will play a role in these lectures, namely the vector multiplet, which is the multiplet which includes the gauge potential. The bosonic content is a complex scalar phi. It's a scalar, so it's the same as a zero form. And it is valued in the bundle associated to the adjoint representation of the gauge group. We have the principal bundle P was a G principal bundle. We consider the adjoint representation of G, and phi is a section of this adjoint bundle associated to P. And in terms of these representations, it is a singlet with respect to all these three subgroups. This is one. Just to indicate this is the quantum number for SU2 plus, SU2 minus, and dimension of the SU2R representation. Okay. The other bosonic field for the vector multiplet is then the gauge potential A mu dx mu. This is a one form or just a element of the set of connections on this principal bundle P. This is also a singlet under the SU2R symmetry, but it's of course a vector in space-time, and therefore transforms as the 2,2 representations of the of SU2 plus and SU2 minus. So now we have 2, 2, 1. Okay. Then we come to the fermionic fields. We have psi I alpha. Here I runs over the SU2R indices 1 and 2 from the two independent supercharges, and alpha is also 1 and 2 from the two-dimensional spinor bundle. This is then a section of S plus. It's in the same multiplet as the Gates potential, so this is also a section of the adjoint bundle of the principal bundle P. Okay. Now just to write this in terms of the representations, we see it here with I and alpha. But that in terms of the dimension of the representation, it's 2, 1, 2. And similarly, we have then the conjugate fields, psi bar I alpha dot. These are elements of the negative chirality bundle, the spinor bundle, and sections of the adjoint bundle. And so here we get quantum numbers 1, 2, 1. Okay, any questions? Okay, there are also auxiliary fields for completeness. These are a complex scalar W, and a real scalar just to close the supersymmetry transformations of shell. They won't play much of a role in these lectures. Then we come to the hypermultiplets. So for these, we can consider a different representation of the Gates group. We will take either fundamental or adjoint representations. These hypermultiplets, their bosonic field content it just consists of scalars. We have four real scalars, or it's combined to two complex scalar fields. We have two complex scalar fields, typically denoted by Q and Q tilde. Of course, this Q is completely unrelated to this e to the 2 pi I tau I had earlier, and I'll use the Q here just to introduce the hypermultiplets. It won't play much of a role later. The Gates transformations on these scalars, they transform in conjugate ways. The Q is transformed to G times Q, whereas Q tilde transforms as Q tilde times G inverse. We can think of Q as a column vector and Q tilde as a row vector in the Gates, in respect to the Gates indices. And so yeah, one way to say is that you have that the hypermultiplet depends on a quaternionic representation of the Gates group. Okay, in terms of these representations of SU2 plus, SU2 minus, and the SU2R symmetry, we get two sets, 1, 1, 2, plus 1, 1, 2. And you can think of the first set as corresponding to Q tilde dagger, and the second representation then in terms of minus Q tilde and Q dagger. These are the four components of our two complex scalar fields. Okay. And in addition, we have fermions. These are denoted by lambda alpha and chi alpha. And these are then sections of the positive chirality spinor bundle times the quaternionic representation of P, either adjoint plus adjoint or fundamental plus anti-fundamental. Representations are 2, 1, 1, and lambda alpha dot dagger chi alpha dot dagger as minus RP in 1, 2, 1. Okay. Okay, so that's a quick review of the field content of the hypermultiplets in four-dimensional n equals 2 theories. We can include, we say usually we have NF hypermultiplets. Where the NF is then stands for the number of flavors. And we can include a mass mj, where j runs from 1 to NF for each hypermultiplet. Okay. And we have an extra symmetry group acting on these hypermultiplets, which gives us a global flavor symmetry. And then this global flavor symmetry, in a sense, rotates these hypermultiplets into each other. Of course, that can only be done if these masses will be all equal. Then you have the symmetric situation. Then the flavor symmetry group is SO2NF. If you have all distinct masses, then you can only multiply a specific hypermultiplet by a phase. So then we get U1, group U1 to the power NF. Okay. Any questions so far? Okay, now I won't go into the details of writing down the action. It's in the textbooks like Weinberg or other textbooks, you can find the precise action for these n equals 2 supersymmetric theories. A specific aspect which is important is the D-term potential. So let me say a little bit more about this. We fix the case group G to be SU2 for now, and also set the number of hypermultiplets to 0. Then we have a D-term potential V of phi, which is 1 over G squared, and then the trace of phi dagger squared. Okay, so to minimize this potential, it's minimized when phi dagger, the commutator, vanishes. And if also to vanish if the minimum of the kinetic term, then phi should be vanishing over the manifold as well. Now, using a Gates transformation, then we can always bring phi to the following form. And the diagonal form, phi is equal to a 0 0 minus a for a complex for some complex number. Okay. Okay, so this phi minimizes the potential. Then the directions which are away, in particular the non-vanishing values for the off-diagonal elements, they become massive with the usual mechanism for spontaneous symmetry breaking. And this happens also for the Gates field. A mu SU2 to Gates field. It similarly splits into, on the diagonal, a Gates field for U1. And then we have off-diagonal W bosons, which are massive W mu plus and W mu minus. And the mass of the W bosons is then given by this by the scalar field A, or this parameter A. It's the absolute value of 2 times A. Okay. That's important. So now it seems that this parameter A is an order parameter on this phase, where the case group is spontaneously broken from SU2 to U1. But since this form of phi is itself not Gates invariant, we should consider a different order parameter, which is the trace of phi squared. Okay, it's independent order parameter. Just the trace of phi squared. And within the full quantum theory, we are then interested to consider the vacuum expectation value of this operator, which is known as the standard notation is the parameter u. And so semi-classically, this goes as 2 a squared, and then there are further quantum corrections to this leading to. So this is the Gates independent order parameter, and this is the order parameter on the Coulomb branch. So this is the branch. The Coulomb branch is the name for this phase of the theory where the gate symmetry SU2 is spontaneously broken to U1. There's also another vacuum space if we have hypermultiplets. So if you have NF larger than 0, actually classically it should even be larger than 1. Then there is also a Higgs branch. Where the gate symmetry is completely broken, then phi is equal to 0, and then the potential says that Qj running from 1 to NF, Qj, Q tilde j, the traceless part, is equal to 0, and the second equation Qj, Q dagger j, minus Qj, Q tilde, dagger j. Again, the traceless part is equal to 0. So then there's a separate potential which leads to these equations for the scalar fields of the hypermultiplet. Okay. Any questions so far? Okay, maybe actually this is a good place to pause for a couple minutes and then start again at 2 o'clock. Okay, thank you. Yeah, feel free to interrupt with any questions. I'm sure if you have a question, then probably someone else in the audience has the same question. So yeah, feel free to speak up. So yeah, we've seen quite a bit in the previous lecture. We went over aspects of non-abelian Yang-Mills fields, instanton solutions, and then we started moving to supersymmetry. We discussed the structure of vector multiplets and hypermultiplets. Now in the supersymmetric theories, an important aspect of these n equals 2 supersymmetric theories is that for n equals 2 supersymmetry, you can have states, so-called BPS states, which preserve still part of the supersymmetry. So they can preserve half the supersymmetries. Preserve half or even all within the and these BPS states, they are protected against deformations of the theory. It makes them often very useful probes because they are not so vulnerable to quantum effects. So what are the BPS states for this theory? One class are these instanton solutions we have already seen. What we saw, these are kind of collective solutions for the Gates field. Another BPS states are the W bosons, as we saw, which have a mass 2a. Another BPS states are the monopoles, particularly the Hooft-Polyakov solution. For which the field phi goes to this form we have seen, A0 minus A for R to infinity, which minimizes the potential. And it has a unit magnetic charge. The mass of these solutions is given by the complex coupling constant tau times the parameter A, which is also the classical. If you include quantum corrections, you will get further contributions. This parameter is then called AD, or the magnetic dual to the parameter A. This is tau A plus further corrections. And then there's an analog. There's actually a whole family based on these monopole solutions. These are the dions, where we add electric charges to these monopole solutions with a magnetic charge 1. Maybe I'll add this explicitly. This is unit magnetic charge. And then the dions have electric charge N. And then their mass reads as follows: tau times A plus 2 to N times A. Okay, so these are the so-called single particle BPS states. In the single particle spectrum, there are no BPS states with magnetic charge 2, for example, for this sphere with NF is equal to 0. I'm still working as before the break, in case NF is equal to 0. Of course, you can consider bounds. You can consider combinations, but these are not single particle states. Okay. Are there any questions so far? Okay, I would like to explain a little bit next about the running of the coupling in this supersymmetric Young-Mills theory. We will see an interesting interplay, in fact, between these parameters A and AD and the complexified coupling tau. You're probably familiar with the fact that in QFT, the coupling G becomes an effective coupling, and it depends on the energy scale you're working with. Coupling G. Dependent on scale E. So we get G as function of the energy E. And similarly, so we can run this for this complexified coupling constant. We get a running or effective coupling tau. So tau of E is the UV coupling, of the parameter you assign it to be for the theory from the outset. But then if you start to include quantum corrections in this theory, you'll see that this is effectively, this UV coupling is effectively modified by a logarithmic term, which has a coefficient C. I'll comment on the coefficient. And this logarithmic in the energy. And the UV scale you start out with when you set up your theory. And then there are you find further non-perturbative corrections. You can show actually that with this case of n equals 2 supersymmetry, that the perturbative corrections, they stop after this one loop term. And then there are further non-perturbative corrections, which are due to the instanton solutions, in fact. This dependence on the energy follows from the beta function. Dependence is characterized by the beta function of the theory. So we get beta of E is writing it in terms of the coupling G derivative to G dE. And it takes the following form. It starts with a term of order G cubed divided by 4 pi squared. Then in the brackets, we get the following combination: a number C, which is determined by the adjoint representation, minus a number C, which is determined by the representation of the chiral multiplet in n equals 1 language. So the n equals 1 supersymmetry has chiral multiplets. They just consider of a scalar, complex scalar, and associated complex fermion. Just like with the hypermultiplets, we can assign a representation for the Gates group, and that's this representation R. So R is the Gates group representation of the n equals 1 chiral multiplet. And you can determine these for our example of SUN. Then C for the adjoint representation is N. And C for the fundamental representation is 1/2. Okay. So if you do the parameter counting, then the n equals 2 vector multiplet includes n equals 1 chiral multiplet in the adjoint representation. So that gives you an n. And then a hypermultiplet gives you 2 copies of an n equals 1 chiral multiplet. So that the two, if you have a fundamental if you have a hypermultiplet in the adjoint representation, this will give you 2n. Okay, so just recall a few aspects. If this coefficient c is larger than 0, then in the limit where the energy goes to infinity, g of e goes to 0 because of the overall minus sign, and the theory is asymptotically free and therefore well defined. At high energies, if we have c is 0, then we have a conformal theory, also well defined. Whereas if we have c is smaller than 0, then it can be the theory of an effective theory, but it is not well defined for large energy. So we have this difficult behavior that g goes to infinity for e to infinity and not asymptotically free. So we are mostly interested in these we are interested in these first two cases. We see here for the conformal case, when this coefficient is equal to 0, that's either in the one hypermultiplet in the adjoint representation, then we get free n minus free n because of the hypermultiplet, and then the 2 in the hyper and 1 in the vector. Or we can have up to 4 fundamental hypers. We get then due to the one chiral in the vector multiplet, we are left with 2n, and then we so that we can with four fundamentals we get precisely 0, and if we take fewer fundamentals, we are in the asymptotically free situation. Okay, any questions? Okay, now in this case where we are on the Coulomb ends of the theory, where we have broken the case group from SU2 to U1 by a web of this field phi. The role of the energy is now played by this parameter a, such that tau as function of a will then take the following form: tau uv minus c over 2 pi I log a divided by lambda uv plus further corrections. And I'm not sure I indicated here that this number c is actually precisely this term in brackets here. Okay. So we can simplify this a little bit, kind of remove the dependence on these UV parameters by introducing an effective scale. You can write it as minus c over 2 pi I times the logarithm of a over lambda plus further corrections. So here we have introduced an effective scale lambda, which satisfies that lambda to the power c is equal to lambda uv to the power c times QUV, where QUV is the Q parameter for the UV coupling constant. Okay. So in a sense, yeah, we see that we get an interesting function for tau in terms of A, which later we will actually try to invert to get the function for A in terms of tau. Okay. Now the effective action, low energy effective action for this theory on this Coulomb branch is determined by a holomorphic prepotential due to the n=2 supersymmetry. So this depends on A and the scale lambda, and it's homogeneous of degree 2. In these two parameters. Fa lambda, the leading term, looks as follows: C over 4 pi I A squared log A over lambda. Then there are further corrections. And the dual variable AD, the mass of the monopole, is given by the derivative of F to A, and the coupling tau of A, effective coupling, is given by the second derivative of F to A squared. Okay. Any questions so far? Okay, so there are all these non-perturbative corrections, which I've just indicated with these dots so far. And as you can imagine, usually non-perturbative corrections are hard to determine. So it was a big development in the 90s when a solution was found by Seiberg and Witten, which determined all these non-perturbative corrections exactly. And the way this was done is by introducing an auxiliary elliptic curve. And that elliptic curve, that periods of the elliptic curve will precisely determine all these corrections. So let me review this a little bit. I'll just focus on the theory without any, still with an F is equal to 0 or without hyper multiplets. This is a Seiberg-Witten solution, gives a full solution for Fa lambda. In terms of an elliptic curve. And the complex structure tau parameterized by U. Call it U was given in terms of A, our order parameter on the Coulomb branch. So these can be interchanged a little bit. U is independent of the transformation of A going to minus A. And striking that the complex structure tau is precisely to be identified with this complexified coupling tau. So it's a good kind of coincidence of notation that on both sides these parameters are denoted by the same symbol. Okay, so let me specify this a little bit in more detail. So we have this space for the order parameter u, which we denote as the u plane, and now for each point in the u plane, or almost every point, I'll get to that, we have an elliptic curve. And the elliptic curve is parameterized by u. It's mathematically known as a local system. Another way to kind of characterize an elliptic curve is as a lattice, or as this parallelogram, where we have a complex structure tau, which is then also parameterized by u. We can explicitly write down the equation of this curve in projective space as an algebraic variety. To this end, let x and y be coordinates homogeneous coordinates on CP2. And then sigma u is the following subspace of the complex projective space, namely the points in CP2 satisfying this algebraic equation: y squared is equal to x times x squared minus ux plus or minus 1/4 lambda to the 4th. Okay, so that's where we see explicitly this dependence, that the curve is dependent on this parameter, on the order parameter u. It explicitly appears here in the algebraic equation for the curve. And if we change u, then we'll change the shape of this elliptic curve. Okay, any questions here? This is not the full, doesn't give us the full information yet. In addition, we should we have an say how are A and AD determined. These are determined in terms of cycles. So we choose A and AD are periods of a one form lambda over 2 cycles A and B. 2 cycles A and B. So we have A, parameter A is the integral over A of the Seiberg-Witten differential lambda, and we have AD is the integral over the cycle B of the Seiberg-Witten differential lambda. We can be a little more precise here. We can write the algebraic equations sigma u y squared. We can look at the zeros on the right hand side. x1 minus x2. Easy, straightforward to determine the roots of this equation. And then we can represent this curve as a double cover. For the coordinate y, for each value of x here on the right hand side, we have two values of y with a plus and a minus sign differing by a sign. So this gives us two sheets. We have a sheet, a plus sheet, and then a minus sheet. So this is the domain of x. And we can plot these roots of this equation. We have here 0 and x1 and x2 and 0 x1 x2. If you look at the so for a weak, if we consider a weak coupling, let's consider a weak coupling. We go back to our coupling constant here, tau. For weak coupling, the imaginary part of tau is very large. It diverges because of the complexified part was going as I over g squared. If g is very small, then we go to very large imaginary part of tau. Therefore, we find that A is very large, and therefore U is very large. So at weak coupling, weak effective coupling, then U is very large. If we look at the roots of this equation, we get one root which goes as U. And then there is another root whose leading term in the large U expansion goes as 1 over U. So x in the weak coupling, x1 lies close to 0, and x2 kind of diverges to infinity. Okay, we can take the branch cuts then as follows between 0 and 1, and then from x2 to infinity. This corresponds then that the cut of the square root will be across the positive real axis. And then we can form the A and the B cycle as follows. The A cycle goes around the cuts 0 and x1. And the B cycle goes from x1 to x2, then continues to the other sheet, goes from x2 to x1, and then goes up. So we get two cycles which intersect each other one time. We can draw it here as follows. We have an A cycle going like this, and then a B cycle goes around like this. Okay. Then if you consider these integrals, you run into the subject of elliptic integrals and use the technology of those integrals developed long ago. Any questions? Okay, now there are two special points here. If we I said for u to infinity, basically this x1 moves closer to 0. It's also possible to go to a point where x1 merges with x2, and then we see that this B cycle will have pinched off. So this happens when U is equal to lambda plus or minus lambda squared. Sigma U is singular. For U is equal to plus or minus lambda squared. So at these points, let's say lambda squared minus lambda squared, and then we get the curve will look like this. Sorry. Where the B cycle has pinched off. I made a slightly different representation as here. This is clearer to draw, easier to draw an elliptic curve where the A cycle in this representation has pinched off. But that's symmetric. So the curve there becomes singular. And what happens here physically is that either the dion at one of these points, at another point it's either the monopole or a dion, if n is 1, has become massless, has become massless. And as a result, the effective field theory breaks down. Field theory not valid. At this point. In the effective field theory, you have integrated out those massive states, monopoles and the dions with their masses proportional to tau A or tau A plus n times A to n times A. Now we have come to a point where those masses, by the mass vanishes for one of these states. So we should this is no longer proper to integrate out these states. We should include them in the low energy theory. So that's the physical origin for these singular points. Okay. Any questions? Okay, so we see we find that this solution of the prepotential that fully determines the effective action for when it goes to supersymmetric theory is fully determined now by this family of elliptic curves, and an important part of the theory of elliptic curves are modular forms, which will play a big role for kind of evaluating these topological correlation functions. So let me briefly review a few aspects of modular forms to explain this connection. It's interesting that this is quite a different subject in mathematics, which plays a big role in this subject. Okay, so a modular form is an analytic function in complex analysis. Is one way to view it. It satisfies a number of special properties. In particular, it's characterized by its so-called weight W. It's a function f from the upper half plane to the complex numbers, such that if I make a change of the argument of the following very specific form, f is the argument is normally tau, but now I change it to a tau plus b divided by c tau plus d. This should almost come back to its to the original function. Now, what are these a, b, c, and d? They characterize an element of the group SL to Z. A, B, C, and D. An element of SL to Z. So simply the matrices, 2x2 matrices with integer entries, and such that AD minus BC is equal to 1. Okay, now this is a little bit too strong. We would like to have a bit more freedom, and to for the functions which actually appear, we get a factor which is determined by the weight. It's c tau plus d to the power w. And then there's a bit more variety. We can have a phase. The whole thing is then multiplied by a phase, epsilon gamma, multiplying this factor of the weight. This is called a multiplier system, and gamma is the shorthand for this element of SL to Z. Okay. Any questions so far? Okay. So let me just give a few examples, familiar examples. One example is the delicate eta function, eta of tau. It has a specific prefactor, q to the 1 over 24, with q still being e to the 2 pi I tau, and then an infinite product of 1 minus a q to the n. Okay. Another example are the Jacobi theta series. They don't transform right under. This one transforms under the full SL to Z. The Jacobi theta series, which I will introduce now, they transform only under a so-called congruent subgroup, a little smaller group than the full group. But they map to each other under the elements in general elements of SL to Z. So they take the following form: theta subscript 2 is the sum over half integers q to the n squared over 2. Theta 3 is the sum over integers q to the n squared over 2. And theta 4 is again the sum over integers, but now with a minus sign inserted. Okay, and you can use the technique of Poisson resummation to show that these Jacobi theta series are transform as a modular form, at least under a congruent subgroup, or transform to each other under an element of SL2Z. And then using the Jacobi triple product formula, you can relate actually to eta and show that eta is also a modular form. Is I think the easiest way to proceed. Okay, yeah, I'm not planning to go too much detail here. I think it's quite well described in various textbooks, but I'm happy to give more detail if people are interested. I am introducing these functions here because, as I said, the Seiberg-Witten solution allows to determine quantities of the theory completely explicitly and to all orders. For example, this order parameter u of tau can be shown to be given by the following form: theta 2 of tau to the power 4 plus theta 3 of tau to the power 4 divided by 2 times theta 2 tau squared and theta 3 of tau squared. So this that fully completely determines u as function of tau to all orders. And one way to show this is to express the curve in terms of Weierstrass. In terms of its Weierstrass form, then you can relate it to the J function and demonstrate that u is given by this function in terms of the theta functions. You can just, of course, make an expansion to see it. If you make a recoupling expansion, what are the first few terms? You'll find that the first term is 1 over 8 q to the minus 1 over 4. Then the next term is 5 over 2 q to the 1 over 4, etc. Okay, and one can show that this function is left invariant under a congruent subgroup of SL2Z, as I already mentioned in words. It's a so-called Haupt module. So u of tau is invariant under the congruence subgroup gamma 0, 4, which is given as follows. There are these elements of SL2Z with the additional constraint or requirement that the upper right corner B is equal to 0 modulo 4. Okay, so we can see that here, that because we get these fractional powers in the numerator, that we have to shift by 4 in order to map it back to itself. That's one way to see that. Okay, any questions? So we see we get the if we shift by 4, then the function you get the same value. So that makes sense then to look for a fundamental domain on the upper half plane on which is 1-to-1, which such that u only takes one value in its in the image. So this is naturally then the fundamental domain H mod gamma 0, 4. So its domains are known as modular curves. And we can construct it as follows. We plot our upper half space H. Then there is a domain. There's a so-called keyhole fundamental domain for SL2Z. Looks as follows. Here, this is symmetric around 0. And this is a half plus I square root of 3, and this is minus a half plus I times the square root of 3. This is the domain H mod SL2Z. The J function, this is a fundamental domain, for example, for the J function. Now we have a gamma 0, 4 is smaller than SL2Z. And there are in fact six elements. We get it's a 6 to 1 map. So the fundamental domain for H mod gamma 0, 4 takes the following form. One example is the following function. We get this vertical axis, then we get the vertical axis at, this is minus a half at 3.5, 3.5. Then we have, so these, I color code the sides which are identified with each other. Now this side goes down, is identified with this side. We also have a cusp at 2. This goes here, this goes there. Then we have an arc here, is identified with this arc. And that's the domain. So you can fold this and you get, in a sense, you can say a free punctured sphere with one puncture here at infinity and these two punctures. And these two punctures here are precisely the points, the singular points where the theory became the effective theory broke down and where the curve becomes singular. So this is u is equal to lambda squared, and here we have u is equal to minus lambda squared. Okay, so now we have, as we will see later, we have basically, we can change variables from the order parameter u to tau, because we have a one-to-one map from this domain in the tau space to the domain for u or for the u plane. Okay, and I should say it becomes a bit more involved, but this kind of aspects are also well developed for the other theories. If we include hypermultiplets, one can also set up a curve, as we have seen here, which now besides u will also depend on the masses, and one can also arrive at these type of fundamental domains, which then such that you get a one-to-one map from the order parameter to the space of coupling constants. Okay, this actually brings me to the end of what I wanted to discuss today. So maybe I'll pause here for questions.